Hello, this is Professor Kuehn, and welcome back to my lectures on electricity, magnetism, and light. We have been studying John Tyndall, his 6 lectures on light, and we are up to about page 271 in A Student's Guide Through the Great Physics Texts, Volume 3. You might recall in my last lecture, I talked about different methods of polarizing light. So we talked about how a thin layer of tourmaline crystal can be used as a polarizer. You can also polarize light by reflecting it from a surface at a very special angle called Brewster's angle. And then at the beginning of this chapter, chapter 23, Tyndall talks about an invention by a Mr. Nickel who developed something called a nickel prism or a nickel crystal, which was also another method for polarizing light, or rather filtering unpolarized light and extracting from it a purely polarized ray. And he mentions that this is a particularly effective way of filtering light into a polarized component. So he's going to mention using a nickel crystal, but you might just think about that as a polarizer. What I want to focus on in this lecture is something I talked about this week, and I thought it would be probably worthwhile putting together a YouTube lecture on this because it's a fairly challenging thing to understand. And it's what we studied in the laboratory this past week, and maybe I'll put up a couple of images if I can develop some images in the next couple of days. But the idea is that if you have two polarizing filters that are crossed, that is crossed polarizing filters, they'll block the light. So you won't have any light that makes it through. But as you noticed in the laboratory, if you put a very thin layer of mica between those two crossed polarizers, suddenly you'll be able to see light making it through. And in particular, if you use a very thin layer of mica, that light will be colored. This is something that Tyndall talks about on page 271. He says, the two nickel prisms play the same part as the two plates of tourmaline, the crossed filters. Placed with their directions of vibration parallel, the light passes through both, while when these directions are crossed, the light is quenched. Introducing a film of mica between the prisms, the light, as in the case of the tourmaline, is restored. But notice, when the film of mica is thin, you have sometimes not only light, but colored light. Our work for some time to come will consist of the examination of such colors. So over the next 3 pages, what Tyndall does is tries to explain, using the undulatory or the wave theory of light, how it is possible for colored light to pass through crossed filters when a birefringent material such as mica is placed between them. In lab, perhaps the most striking thing was when we placed a bit of cellophane tape on a sheet of acetate and located this between the two crossed filters and restored, or were able to see, the colored light coming through. So what I'm going to do is I'm going to explain this in a way that's a little bit different than the way that Tyndall explains it, with some 3-dimensional drawings. So here I go. So what I'm going to do is I'm going to draw here a set of axes so that we can more conveniently talk about the phenomenon that Tyndall is referring to. So let's draw a z-axis like this. This is going to be somewhat of a 3-dimensional drawing if I do it right. Here is going to be our x-axis, and here is going to be our y-axis. And let's suppose that unpolarized red light is traveling along the z-axis. So I'm going to signify that this is unpolarized by denoting a line that's oscillating along the x-axis and along the y-axis. Again, what this represents is as the beam is traveling along the z-axis, there are vertical vibrations of this transverse wave along the y-axis and horizontal vibrations of this transverse wave along the x-axis. Of course, for it to be unpolarized, there's transverse vibrations in every orientation in the xy plane, but even the diagonal vibrations can be decomposed into components along the x and y axes. That forms a basis, so to speak, in which you can write the directions of the vibrations. Okay, now this light, to be specific, let's say this is unpolarized, which is what I just mentioned, and let's suppose that it is monochromatic red light with a wavelength of, let's say, 633 nanometers. Okay? And now let's imagine that it strikes a polarizing filter. So I'm going to imagine we put a polarizing filter right here in front of it. And let's suppose that this polarizing filter is oriented so as to only allow light that is polarized along the x direction, and it quenches or extinguishes polarization vibrations along the y direction. If we do this, well then, the light that makes it through this is going to be purely horizontally polarized, and that's what I'm indicating here. So I'm going to make a head-on drawing of this just to make a point here, and you'll see why I'm doing this in a minute. So this is a head-on view looking down the z-axis, and we have this light that's vibrating horizontally. So I'll draw at a particular moment in time the vibration, let's suppose, is to the right in this direction. And so that would be in the positive x direction. And why don't I just draw this coordinate system just to make it easier to understand what I'm talking about. This is the x direction and the y direction. Now, any vector or any arrow or any vibration to the right along the plus x axis can be decomposed along another set of axes, and that's what I'm going to be doing. I'm going to draw some diagonal axes for reasons that will be clear in a moment. And let's suppose that we project this vibration onto this axis and onto this axis. That being the case, this horizontal vibration can be understood as comprised of a vibration that takes place along that diagonal plus a vibration that takes place along that diagonal. Okay, so it's a bit like saying if I'm traveling in the northeast direction, that can be described as partially north and partially east. Well, if this vibration is along the x-axis, it's partially along the diagonal upward and the diagonal downward. This will become important as we start talking about the orientation of the birefringent crystal. Okay, so now let's suppose that this horizontally polarized light strikes a thin film of birefringent material, and I'm going to make it look a little bit thick just because it's easier to draw. So I'm going to draw a layer of this birefringent crystal right here. And let's suppose that this birefringent crystal is oriented in such a way that the crystal axes, and I'll say more about this in a moment, are oriented diagonally, or as Tyndall says, an oblique orientation compared to the polarizer. Okay? Now, what do I mean by that? Well, any kind of birefringent material is called birefringent because it has two different refractive indices. That is, for light that's polarized in the direction of one of the crystal axes, it experiences one refractive index. And if the light that's incident upon it is polarized in the other direction, that is along the other crystal axis, it experiences a different refractive index. So there are two different refractive indices of this birefringent material. And this birefringent material we could use mica or selenite, as he mentions, or Scotch tape. Let's go ahead and imagine we're using some kind of cellophane tape, and I'm just going to use some numbers for the two different refractive indices. So the refractive index along the fast axis, and I'll explain what I mean by that in a moment, is, let's suppose it's 1.544. And let's suppose the refractive index for light polarized along the slow axis is 1.553. Okay, now why are these called the fast and slow axes? So let's suppose if the light is polarized along this axis right here, that would be the fast axis. And if it's polarized along this axis, let's suppose that's the slow axis. Okay, so notice that for the slow axis, the refractive index is larger. That implies that the speed of light is slower, because you might recall that the velocity of light in a medium is equal to the speed of light divided by the refractive index of that medium. So the larger the refractive index, the slower the beam. So I'm just kind of saying this to jog your memory that the velocity of light is related to the velocity of light in a vacuum or in air, because air is pretty close to a vacuum, divided by the refractive index of that medium. So the point is, and here's the main point, is that if this light that is incident upon this birefringent material is polarized along the horizontal or the x direction, that can be considered as having a component that is polarized along the fast axis of the crystal and a component that is polarized along the slow axis of the crystal. And those two rays of different polarization will travel at different speeds through this crystal. And if they travel at different speeds through the crystal, by the time they travel all the way across the crystal, they will have gone through a different number of oscillations, because remember, the wavelength in a medium is different when it's traveling at different speeds. So the point is that, again, if this crystal has some particular thickness, let's call that thickness D, by the time these two different polarizations have gone through that thickness D, they will be out of phase potentially with one another. How much they are out of phase with one another depends on the thickness of the crystal. And so let's set up a particular condition. Let's say we want to find the thickness of this birefringent material so that one of the waves has traveled through an extra half of a vibration compared to the other. Okay, so we want this material, this birefringent material, to be a so-called half wave plate. And that means we want the oscillations, that implies we want the two distinctly polarized beams to be out of phase with each other in this problem, at least, by 180 degrees. What does that mean? It means that if you're going to count the number of oscillations of the one polarized along the fast axis and count the number of oscillations of the beam polarized along the slow axis, the difference in the number of oscillations should be equal to 1/2. Okay? So again, this is the difference in the number of vibrations executed by the beams polarized along the fast and slow axes of the crystal, or of the birefringent material. Okay, so that's kind of a stipulation that we're setting for this to be a half wave plate. That's the stipulation. What do we mean by delta n? Well, we're basically saying that delta n, that's a difference, is the number of oscillations that the wave polarized along the slow axis undergoes minus the number of oscillations that the wave polarized along the fast axis undergoes. Okay? And we want that to be equal to, again, 1/2. Now, what is the number of oscillations that the wave polarized along the slow axis undergoes? Well, as I mentioned in class, if you want to count how many oscillations, you will need to know the thickness of the crystal and the wavelength. So it's almost like if you were, let's say, 5 feet tall. This is an analogy that might help you understand this. If you know that you are 5 feet tall and a tennis court was 50 feet long, how do you figure out how many of you lying down would fit in that tennis court? Well, you take the 50-foot long tennis court and divide by your length, 5 feet, and say 10 of you fit on the tennis court. Well, similarly, if we want to know how many wavelengths fit into this crystal, we're going to need to know the thickness of the crystal, which we specified as d, divided by the wavelength of the wave, and in this case we need to put a subscript s because the wavelength of the wave traveling the slow axis has a wavelength lambda sub s, which is going to be different than 633 nanometers. Likewise, the number of oscillations of the wave polarized along the fast axis can be written as d over lambda fast, and that should be equal to 1/2. Okay? Now, let me remind you of something. All that we need to do here, remember we're trying to solve for d, so let's go ahead and factor out the d. d times 1 over lambda s, we're just doing some algebra here, over lambda f equals 1/2. So we factored out the d. Now let's solve for d. d is going to be 1/2 times 1 over 1 minus lambda s minus 1 over lambda f. Okay, so this is what we're trying to solve for, the thickness, so that these two waves are exactly out of phase with one another. Now, how do we figure out the wavelength of the wave polarized along the slow axis. How do we figure out the wavelength of the wave polarized along the fast axis? Well, that's pretty easy. Remember how we do this. What we can do is say the wavelength for the wave polarized along the slow axis is going to be the wavelength in a vacuum or in air, they're pretty close to the same, divided by the refractive index of the wave polarized along the slow axis. Okay, and notice that because n sub s is larger than 1, that means the wavelength is going to be smaller than it was in the air. Basically, in this material, the wavelength is shorter. And likewise, the wavelength for the wave traveling along the fast axis is going to be the wavelength in air divided by the refractive index of a beam that is polarized along the fast axis. So we can plug those into our formula, say d equals 1/2 of 1 over, and here we'll have n sub s over lambda minus n sub f over lambda by substituting those into our previous formula. And now the nice thing is we can factor out the 1 over lambda from the denominator. So this is a little bit of algebra here. And now we can simplify this a bit more and say lambda over 2 times 1 over ns minus nf. And because we know the refractive indices, we can plug these in. And when we do that, we can get that the thickness of the crystal is 633 nanometers divided by 2 times 1 over 1.553 minus 1.544. That's plugging in these numbers. And when I do this, I got the distance to be 35.2 micrometers, or 35.2 microns. So that would be the answer to this question. Remember what the question was. It is, how thick does this material have to be so that these two waves that are traveling through with different polarizations are exactly 1/2 of a wavelength out of phase with one another? Okay, how thick is this? Remember, you did measurements of your hair. Your hair is between about 50 and 100 microns thick. So this is a little thinner than your hair. Okay, now, what does this imply? Let's go back to our original drawing up here and think about what the waves look like coming out. So whereas before, and this is going to be a little bit tricky to understand. So remember before, when you had the horizontally polarized light could be decomposed into a component that was upward diagonal and downward diagonal. That comprised the horizontally polarized wave. But now, because one of those is 1/2 a wavelength out of phase, the one that was vibrating up like this, let's suppose at the moment it's vibrating up and diagonal, whereas the other one had been vibrating down at a diagonal, now it's gone through an extra 1/2 of a wavelength, so now it's vibrating up and at a diagonal. Okay? And if you put these two back together, you can sum those. As a result, you'll get, and let me make this maybe in orange to, I'll still make it red. When you sum those, you get something that is vibrating upward. And likewise, when the one on the upward and right direction has progressed to vibrate down, the one upward and left will also be down, and so it will be vibrating straight down. In other words, you will have a wave that is vibrating with vertical polarization now. In other words, the wave that comes out of this crystal now is vertically polarized light. So whereas when it was coming in, it was horizontally polarized, by the time it has gone through this birefringent material, it will now effectively be vertically polarized. And thus, if you put another polarizing filter over here that is oriented crossed compared to the original polarizer, then that vertically polarized light will make it through. So what has happened here? Essentially, this half-wave plate, this thin 35 micron thick layer of birefringent material is just thick enough to rotate the plane of polarization of this initially horizontally polarized wave by 90 degrees, so now it's vertically polarized. Now, think about the implications of this. What this is saying is that if you have two crossed polarizers and nothing between them, and unpolarized light strikes them, normally the cross polarizers would transmit no light whatsoever. But if you put this birefringent material between them that's just the right thickness, then you will suddenly be able to see through them. This is precisely what you noticed when you put a layer of mica between your cross-polarizing filters in the laboratory. Suddenly it could transmit light. That's what we're saying here. Now notice in my example, I used specifically red light. And the red light has been rotated, the polarization of the red light has been rotated by 90 degrees in order to make it through that polarizing filter. But if you look back at our formula that we developed, the thickness that's required for it to rotate it by that amount exactly depends on the wavelength of the incident light. So in other words, if you were to use a different wavelength of light, let's say light with 3/4 of the wavelength, maybe blue light, the thickness would have to be about 3/4 as big in order for that to be rotated by 90 degrees. So depending on what kind of light you want to transmit through these cross polarizers, you need to make birefringent materials of different thicknesses. This is precisely what you did when you took cellophane tape and layered it to different thicknesses. You noticed that when you passed white light through cross polarizers with a different layer of tape between them, or different thicknesses of tape between them, different colors of light appeared in the different regions where the tape had different thicknesses. That's because the thickness of the tape in a particular region dictates what color of light is able to pass through the cross polarizers. And that's precisely what Tyndall is talking about in this section. Now, I realize that this is somewhat of a complicated explanation of this phenomenon. I wish there was a clearer explanation. I don't know what that would be. The fact is, nature is sometimes complicated. But it's also, remember, what we saw in the lab was a very beautiful phenomenon, and we're trying to come up with the clearest, most self-consistent explanation that we're able to. And that's what I've tried to do in this lecture. Let me just say one other point, is that we've built, in this case, a half-wave plate. That is, a plate that's exactly thick enough to rotate the plane of polarization by 90 degrees. You get an interesting case when you make what's called a quarter-wave plate, where the two different polarizations are a quarter of a wavelength out of phase with one another. If that's the case, then the light that's impinging upon the crystal, the horizontally polarized light hitting this crystal, when it comes out, will be circularly polarized. That is, the plane of polarization will be spinning around the z-axis as it progresses.